Hi, this is Johan again from Ganister. So this is a follow-up video on the first presentation we've made for this options and variant test bench for Ganister. So if you want to see first, I'll put the link to the first video. Here, I just wanted to precise a few things, and in the first video, all the rules that we were using were just created with two options. So I wanted to give you a better insight of performances when we add options and how it works. So let's create a few options without really smart names. A, B, C, D, E, F, G, H. It's 8. So potentially if you have 8 variables, this means 256 possibilities. If you have, so this will create potentially a rule with a large matrix if you add all these. So we have this capability to change the display, so you have a better visibility on the matrix. So of course, this is not the best way to understand what has to be, what rule we want to set. For now, we just know that if you go from left to right, 1, 2, 3, 4, 5, 6, 7, 8, this is equal to H, G, F, E, D, C, B, A. And so we work on having something that is better, easier to understand, even though this is not the UI that will be implemented in Ganister. So that's more, or it may be reused, but as is, it's not what we are going to use. So here, what I wanted to show is first, so if you have this larger matrix, you can still build these rules. So the fewer forbidden points, the simpler the formula will be. So if we say solve expression, you have the expression here. So if we have more here, let's put randomly some forbidden points. And this is what has been created. So we, in this test bench, the calculation is done client side. If we really sum more rules, if we have like 10 rules like this, when you will run this configurator, just calculating the rules may take a little bit more time, but not when you actually play with the form. It's just to prepare the form, it may take a little bit more time. So the code, and that's the great thing about Ganister and our developments, is that we use JavaScript on the server and on the client. So we actually initially created this feature on the server. So we have the code on the server. We adapted it to have it for our test bench on the client. So when we do it on the server, to accelerate the calculation, because that's a lot of processor or processing time, it can either be splitted into different threads. So the performance then will depend on your computer and on the server computing power. That's one thing. We could also start functions as a service on a remote cloud function, which is, it could be limited in terms of calculation, but you can launch a lot of actions like this, and this could be available for anyone, which would be interesting. So in terms of performances, we've had the first thing we wanted to test was the computing performance. The other thing that we wanted to make sure is that when sometimes in assemblies you have a lot of options, and let's say for this one we have 8 options. So the typical answer or the typical explanation from someone who works on this is like, yeah, we're going to have 256 possibilities. Well, usually not, because usually there's definitely options that may not exist, or rules that, or configuration that will not exist. And sometimes it's just A can't be with B. And so if A can't be with B, then maybe half, or you go down to 64 options or configurations. And so what we like to do with these matrices is be able to detect whether options have been used in the same matrix, but they may not be correlated or related. And it reduces dramatically the complexity. So, for example, for this matrix, there are 256 points. If we were able to demonstrate that maybe A, B, C, D are independent from E, F, G, H, instead of having 256, we would have 2 times 2 power 4, 2 times 16. So it's going to be 32 configurations instead of 256, just because we were able to demonstrate that these options were independent. So let's see, for example, if we say this is an impossible for example 0001, so just having A set to 1 and B, C, D set to 0, if we say this is impossible, then the whole column is impossible. Let's do the same thing for H, G, F, E. Let's say that E, it's by itself, if H, G, F are null, then we can't have E set to true. So let's say this is impossible. So on purpose, I won't show I just want to show this. So let's say solve expression. And so you see we have run one expression here, but our code will detect that this is what we call a product of sum. So a product with the N and sum with OR. And so it allows us to see that here we see D, C, B, A, and here H, G, F, E. So there is no relationship between these two. And as this is a product, then we can have 2 separated rules. So if we go down, you can see that the computed rules create this. If we had something in common, let's say this maybe, no, this is still creating independent, but you can see that the independence is now more complex. But this is the goal of this, and we could actually display that we came from 256 possibilities to 32 possibilities, just by detecting what is independent in the formula. That's very important in terms of performances for us. So here we said 0001 is impossible. So if we go in the configurator, 0001, that might not be this one. Let's go back here. We said 0, D, C, B, A, H, G, F, E, H, G, F, E. Yeah, that's right. Okay. Yeah, if you only have zeros, you can have E here. And that's something we discussed. I discussed a little bit in the last video. Is in terms of UI, in some cases there's just one possibility. If, for example, in our previous example, in the previous video, if you have convertible, you can't have the antenna. So switching on convertible switches off the antenna because there's just one possibility. It cannot, the antenna can't stay. Here, if you have just E, there's no option here. There's no available options where E is set as true by itself. That's based on the rule we define. So the only thing we say, we block the addition and we write not feasible. So that's another UI thing that we've implemented to make sure this is not available. Same thing for A. You see A is not, I could put B. I can put B and A, but I can't remove B because A is blocking it. So I can remove A, and here I'm blocked. All right, so that was a few more explanations on the UI, the performances, and what our code is doing. So it's not just solving this matrix into a formula, it's also taking care of how can we reduce the complexity of a model by detecting independent options through the rules that have been defined.